This is section 6.3, explaining the major features of the solar system. So what caused the orderly patterns of motion? Why are there two major types of planets? Where did asteroids and comets come from? And how do we explain the exceptions to the rules? So what caused the orderly patterns of motion? Well, as I've already talked about, we have something called the conservation of angular momentum. We learned about that in an earlier chapter. And that states that as something comes together closer to the center as it's spinning, it will spin faster due to the fact that it has to maintain that angular momentum. So in the case of this cloud, the rotation speed of the cloud from which our solar system formed must have increased as the cloud contracted. As it contracted, the collisions between the particles in the cloud caused it to flatten into a disk. And this apparently we've seen in other places in space where the same kind of spinning and flattening is occurring with other younger solar systems. This is a good picture of what's happening. This is on page 156, both of these pictures. We have an infrared image on the left which shows a large debris disk orbiting the star Beta Pictoris and what could be a Jovian planet that formed from the disk. And on the right, we have a picture from the Hubble Space Telescope that shows a disk around a star. Colors aren't real, but it's just changing the color so that we can see what's happening here. But again, there seems to be some sort of disk of material that's coming together, coalescing, condensing, and may eventually form a solar system. So why are there two types of major types of planets? As we already know, as you see on the left of the slide here, we have the terrestrial and the Jovian planets. And over on the right, we see what happens with temperatures, condensation temperatures. In other words, the temperature at which a planet might form. Well, we know that the higher temperatures are where metals will condense, so that's at the bottom of the list. Next, rock materials at 500 to 1300 K. After that, hydrogen compounds, and finally hydrogen and helium gas, which don't really condense in the nebula. So there's a natural progression from hotter to cooler temperatures, showing what kinds of things will condense depending on that temperature. The hotter temperature planets, obviously being nearer the sun, are the ones where the rocks and the metal are going to condense first. Whereas the Jovian planets, being farther out, will have a lower temperature where things will condense. There's also something called the frost line. Inside the frost line, it's too hot for hydrogen compounds to form ices, whereas outside the frost line, it's cold enough for those ices to form. So within the frost line, rocks and metals can condense, hydrogen compounds stay gaseous. Beyond the frost line, hydrogen compounds, rocks, and metals can condense. So there's this natural boundary where hydrogen will condense and where it won't condense. That's called the frost line. So what about the formation of the terrestrial planets? Well, we know there's small particles of rock and metal were present inside the frost line. These things called planetesimals of rock and metal built up as the particles collided, and then gravity eventually assembled these planetesimals into terrestrial planets. So obviously gravity had a large part to play in collecting the larger or the rock and metal pieces in the early formation of the solar system. So this is how they accreted or gathered up, I guess you could say. The many smaller objects collected into just a few large ones. Now, this process, of course, would have taken hundreds of millions of years, but this is how we think the planets came to be. What about the Jovian planets? Well, ice could also form small particles outside the frost line, larger planetesimals and planets were able to form, and the gravities of these larger planets were able to draw in surrounding hydrogen and helium gases. So it may have been made of smaller ice particles at first, collecting larger particles, but it's the hydrogen and helium that makes up the majority of the Jovian planets today. So we've got the spinning disk around forming a Jovian planet as smaller chunks of gas or smaller chunks of rock and hydrogen and helium collect. What about the asteroids and the comets? Where did they come from? Well, you could call them leftovers. Instead of everything being collected into either terrestrial or Jovian planets, there may have been some things left over in that process. So we generally have rocky asteroids inside the frost line, icy comets outside the frost line. Leftover planetesimals, things like comets and asteroids, probably bombarded other objects in the late stages of the solar system. And that may be why we see certain places, certain moons, and of course planets heavily cratered. Our water may have come to Earth by way of icy planetesimals from the outer solar system. The amount of water that's on this planet today it's very, very hard to interpret as just that one source. There may have been other sources. Those sources may have been internal. For that, we'd have to turn to geologists. So how do we explain exceptions to the rules? The fact that Uranus is tipped on its side, the fact that our moon is much, much larger in proportion to our planet than any other combination. Well, the unusual moons of some planets may be captured planetesimals. Again, they may be bits and pieces of material that was floating around out there that happened to get captured by the planet. In this case, this is Mars moons, Phobos and Deimos. They may have then accreted into the moon. These planetesimals may have gathered up to form a larger object. So impact apparently has some place in the nebular hypothesis of how our solar system came to be. There may have been large impacts that fractured and did other things to our solar system that we just have no evidence for today. Giant impacts might also explain the different rotation axes of some planets. Again, Uranus is a good example, being on its side like this. Maybe an impact actually turned Uranus on its side. That would have had to have been a major, major impact. So this diagram is a good review of the nebular theory. It's on page 163. So starting from the top, we have contraction of the solar nebula, and then condensation of solid particles. The hydrogen and helium remained gases, but other materials condense into solid seeds for building planets. And then in step 3, we have accretion of the planetesimals. In other words, the seeds stick and collide and form larger ones. And finally, the clearing of the solar system by means of solar wind. The sun not only gives off electromagnetic radiation, it also gives off particles of many types. And that might be responsible for just kind of cleaning out or clearing out the solar system of any remaining material. So, what have we learned? Well, what caused the orderly patterns of motion? We have a solar nebula spinning faster as contracted, and because of conservation of angular momentum, the smaller the disk got, the faster it moved, the faster it spun. Collisions between gas particles then caused the nebula to flatten into a disk, and we have observed such disks around newly forming stars. So we have places out there in space that we've observed with telescopes that apparently have the same mode of formation. Why are there two major types of planets? Well, the rock, the metal, and the ice condensed outside the frost line, but only rocks and metals condensed inside the frost line. Small solid particles collected into planetesimals that then accreted into planets. Planets inside the frost line were made of rocks and metals, and additional ice particles outside the frost line made planets that are more massive, and the gravity of these massive planets drew in hydrogen and helium gases. So there's a very orderly arrangement of things based on the differences between the materials that the terrestrial and the Jovian planets are made of. And where did asteroids and comets come from? Well, they're leftover planetesimals according to the nebular theory. And how do we explain exceptions to the rules? Well, that may be due to many giant impacts, bombardment of newly formed planets by planetesimals. A material torn from the Earth's crust by a giant impact may have formed the moon. The last section of the chapter has to do with the age of the solar system. How do we know how old it is? We can't find the age of a planet, but we can find the age of the rocks that make it up. And we can determine the age of a rock through careful analysis of the proportions of various atoms and isotopes within it. In other words, some things are radioactive when they first form and become non-radioactive as they age. Here's a graph that shows the potassium-argon reaction. Potassium-40 is an element that decays into what's called argon-40, and it does so with within a certain time period. In other words, half of the potassium-40 decays to argon-40 in a half-life, and the half-life of potassium-argon is 1.25 billion years, 1.25 billion years. So if we have a sample, a rock sample, that we can detect and measure the amount of potassium and the amount of argon in the sample, and look at the proportion or the ratio between them, we can actually determine the age of the rock. So age dating of meteorites that are unchanged since they condensed and accreted tell us the solar system's about 4.6 billion years old. That's the oldest material we've found in the solar system. Whether it's a meteorite or comet material or asteroid material, this is the oldest we've found. Radiometric dating tells us the oldest moon rocks are about 4.4 billion years old, meteorites 4.55, so we think the planets formed around 4.5 billion years ago. We have rocks from the moon that we've been able to age date, radiometrically age date, that give us a pretty good idea of when the moon formed, and that would have been part of our solar system. So how do we know the age of the solar system? Well, astronomers use radiometric dating to determine the age of meteorites and rocks, and the technique indicates that planets formed about 4.5 billion years ago.